Okay, today we're going to talk about geometric sequences and series. So we talked a little bit about uh, sequences and series in general, how they're lists of numbers, and there's often a rule that describes the pattern that the numbers follow. Then we talked specifically about arithmetic sequences and series. An arithmetic sequence is one where there is a common difference between consecutive terms, meaning if I take a term and I subtract the one before it, and I do that with any pair of numbers anywhere in the sequence, I will always get the same difference, meaning that we're adding or subtracting the same number between terms every time. So I'm either adding 4 every time, or I'm subtracting 1003 every time. Whatever it is, it's consistent. A geometric sequence is one where there is a common ratio between consecutive terms. So rather than adding or subtracting, meaning if we subtract the previous term, we always get the same number, we will be finding the common ratio by dividing by the previous term. So if we look at these three examples, excuse me, are they arithmetic, geometric, or neither? So the first thing we need to do is check to see if it's arithmetic. You could check in either order, but it's always easier to check arithmetic, so I always start with those. So what did we add to go from 6 to 12? Well, we clearly added 6. Now, you have to check more than one term because I can go from any number to any other number by adding. That will work always. I need to check and see if that pattern continues. So if I add 6 again, do I get the third term? And obviously we don't, right? 12 plus 6 is not 20, so it is not arithmetic. So now let's start dividing them. So let's take 12 and divide it by 6. Well, if I divide by 6, I'm multiplying by 2, right? If I multiply 12 by 2, do I get the third term? Because again, same pattern has to continue throughout the entire sequence. 12 times 2 is not 20. So this one is neither. Right? It is neither arithmetic or geometric. Those aren't the only two options, but they're the only two we've talked about so far. Okay, so let's jump down to the next one. Change colors. 256 to 64. So that's going to be subtracting like 192, right? It's a huge number. Now, obviously, I'm not subtracting 192 to go from 16 to 64. That's not going to work. So it's not going to be arithmetic. So then I start dividing. If we do 64 divided by 256, we'll get 0.25. So it's like I'm dividing by 4. If I divide 64 by 4, then I get 16. And if I divide that by 4, I get 4. And if I divide that by 4, I get 1. This one is geometric because I'm multiplying by the same number every time. We're multiplying by 1/4, which is the same as dividing by 4, but we usually talk about what we multiply by. So we'll call it a ratio of 1/4. Each number is 1/4 of the number that came before it. Okay, so then let's look at the third option. 100 to 92. Now I could divide by something super strange, or we could subtract 8. So let's see if that works. And if I subtract 8 from 92, oh, what do you know? We do get 84. And 84 minus 8 is 76. And 76 minus 8 is 68. This one is arithmetic. And we have a common difference of 8, meaning we are subtracting 8 each time. Okay, so biggest difference. Arithmetic sequences have a common difference, and geometric sequences have a common ratio. Take 30 seconds or however long it takes for you to figure out whether these three sequences are geometric or not. So I'm not asking if it's arithmetic, so all you have to check is the ratio. So go ahead and pause this until you're done. Okay, I'm only checking to see if it's arithmetic, so all I'm going to do is divide. So I'm going to do 9 over 27. That's 1/3. Then I'm going to do 3 over 9. That's also 1/3. If I did 1 over 3, well, guess what? That's also 1/3. Since these ratios are all the same, then yes, this is geometric. The ratio is 1/3. Over here. To go from 2 to 6, what do I have to multiply by? Well, I'd have to multiply by 3. Right? If I multiply 6 by 3, do I get 24? No. So this is not geometric. It's going to be something else. And the third one, what do I have to multiply negative 1 by to get 2? Well, I'd have to multiply by negative 2, right? Make sure it's multiply by negative 2, not subtract 2. If I multiply by negative 2, I get 2. Then if I multiply negative 2, or 2 by negative 2, I get negative 4. And if I multiply negative 4 by negative 2, I get 8. So you see how this pattern's continuing, right? It's flipping back and forth between positive and negative because I'm multiplying by a negative, and the numbers themselves are getting twice as big. So this one is also yes. The ratio is negative 2. Just like arithmetic sequences, we can write a rule for a geometric sequence to describe the pattern and find any given term. So this is what you're going to want in your notes for sure, is this pattern right here, this rule. A sub n is equal to a sub 1 times r to the n minus 1. A sub n means the nth term of the sequence, so any given term. A sub 1, as you might imagine, is the first term. R is the ratio, meaning what are you multiplying by every time? And then n is going to be whatever number of terms down the line we're looking. So if I'm trying to find a sub 9, that's the 9th term of the sequence. So I would find the first term, multiply by the ratio, raised to 9 minus 1. Okay, so here's an example with numbers. The nth term of a sequence with a first term of 2 and a common ratio of 3. So if we were to write out a little bit of that sequence, that would be 2. The ratio is 3, so the next one is 6. The next one is 18, right? And we're just going to keep doing this all the way through. The next term would be 54. We'll just stop there. This is the sequence described by this pattern. First term of 2, common ratio of 3. This would be the rule we would write. A sub n is equal to 2, the first term, times 3, the ratio, to the n minus 1. N is our variable because that's the number of terms we're looking for, and that can change. The pattern doesn't change. The first term doesn't change. What we're multiplying by doesn't change. But which term of the sequence we're looking for does change. Okay, so again, make sure this is in your notes. Make sure it's labeled for geometric sequence. You don't want to get this confused with arithmetic sequence, the rule for an arithmetic sequence. I'm going to go on, but if you need to keep writing this down, go ahead and pause it. Okay, so if we're going to write a rule for these, all right, let's write down that general form again real quick. A sub n is equal to a sub 1 times r to the n minus 1. So we need to identify those things in this first pattern, right? So first term part is easy. That's 5. It's the first term. Times r. What are we multiplying by? What is our ratio? Always think about it as what are we multiplying by. So if the numbers are shrinking, you could think about it as dividing, right? But what we're doing is multiplying. So we're multiplying 5 by 3 to get 15. Multiply that by 3 to get 45. Multiply that by 3 to get 135. So r, or our ratio, is 3 to the n minus 1. Then it says to find a sub 8. So a sub 8, the 8th term of this sequence, is 5 times 3 to the 8 minus 1. I'm going to put a multiply in there. So that's 5 times 3 to the 7th. Now this is super important. Think about order of operations. I cannot multiply the 5 and the 3 yet. I have to do the exponent first. So I need to figure out what 3 to the 7th is. You're going to want a calculator for that. 3 to the 7th is 2,187. Huge number. Now I have to multiply that by 5, so that a sub 8, the 8th term of this sequence, is 10,935. You're going to notice that geometric sequences grow very quickly. Geometric sequences get much bigger, much more quickly than arithmetics do, because I'm multiplying something every time, and every time I multiply it, it's the snowball effect. Whereas in arithmetic sequence, I'm just adding the same amount every time. So it'd be like scooping sand from or into a bucket. With an arithmetic sequence, you're just using the same scoop every time. With a geometric sequence, every time you take a scoop, your shovel gets 3 times larger. So it's going to grow and grow and grow much more quickly. Okay, let's look at B. A sub n is equal to the first term. That'll be 88 times r. So what are we multiplying by every time? We can look at it in terms of division to figure it out, but when we write it down, we need to write it down in terms of multiplication. So what that means is I'm seeing these numbers and I'm thinking, oh, it looks like we're dividing by 2 every time. 88 divided by 2 is 44. 44 divided by 2 is 22. 22 divided by 2 is 11. So I'm dividing by 2 every time. What that means is I am multiplying by 1/2 every time. That's what I'm going to write down for r, is 1/2. I'm also noticing that I'm going from positive to negative to positive to negative. So the only way to do that is if my r value is negative. So really, what I'm multiplying by every time is negative 1/2. 88 times a negative 1/2 is a negative 44, so on and so forth. Okay, and then that number, the negative 1/2, is raised to the n minus 1. So there's our rule. We want to find a sub 8 now. So a sub 8 is equal to 88 times negative 1/2 to the 8 minus 1. So that's 88 times negative 1/2 to the 7th. Again, it could be tempting to multiply 88 by negative 1/2, but we can't do that yet. We need to find negative 1/2 to the 7th. And I can't stress this enough. You're going to need parentheses. Anytime you're raising exponents and there's a negative involved, you want parentheses. So I would type it into your calculator exactly like this. Parenthesis, negative 1 divided by 2. Or you can do 0.5, that's fine too, but make sure it's in parentheses. Close the parentheses, then you can do the caret and then 7, right? And that's going to tell you that this is negative 0.0078125. I'm not going to type that number in. I'm not going to round it. I'm just going to, from my calculator, hit times 88 and just multiply this thing by 88 without typing anything. And that way I use all those decimals and I don't have to worry about any rounding errors. And I get negative 0.6875. If you're interested in the fraction, you can hit Math 1 Enter if you're on a Texas Instruments calculator or you're using the emulator. Remember Wabbit. EMU is a good app for a free graphing calculator. If you have more questions about that, you can let me know. Turns out to be negative 11/16. I would accept the decimal just fine, though. So either one of those would be the 8th term. That's a terrible A of that sequence. Okay. So, yo-yo, I want you to do the same thing for this sequence. 3, 15, 75, 35. Okay, so then find a sub 9. You have to write the rule and then find a sub 9. So pause this for a minute, 2 minutes, whatever it takes, and then come on back. Okay, here we go. We have a sub n is equal to a sub 1 times r to the n minus 1. I'm going to use capital A's because they're easier to write. A sub n is equal to the first term, 3, times our growth rate. So what are we multiplying by every time? Well, to go from 3 to 15, that'd have to be 5. To go from 15 to 75, that's also 5. So my growth rate, or my ratio, my r value, is a 5 to the n minus 1. So there's the rule. But now I want a sub 9. So I'm just going to plug 9 in for n, and then do the calculations. So a sub 9 is equal to 3 times 5 to the 8th. Again, that cannot be 15 to the 8th. 3 times 5 to the 8th and 15 to the 8th are not the same thing. If you don't believe me, type it into your calculator. So we got to do 5 to the 8th first. Spoiler alert, it is not a small number. So 3 times 390,625. Then I'm just going to hit multiply by 3 so that we find that the 9th term is 1171875. 1,171,875. Like I said, geometric sequences grow very quickly, so these numbers are going to be huge. Okay, kind of a little twist on it. We're getting a sequence down, or a number that's partway down the sequence, but we don't know the first term. So I know that the 4th term is 12. The ratio is 2. I want to find the nth term, so just write the general rule, and then graph the first 6 terms. So here's our general form. It's always a good place to start here. Let's just plug in what we know. Well, I know the nth term, or the 4th term, is 12, so that's a term. I don't know the first term. The growth rate is 2, and to get 12, n had to be a 4, right? Because that's the 4th term is 12. So if I make the n a 4, now I can solve for this first a here. 12 equals a times 2 to the 3rd. 12 equals 2 to the 3rd is 8, so that's 8 times a. Divide both sides by 8. The first term, a, is going to be 12 over 8. Or when we reduce that, 6 over 4, 3 over 2. So a sub 1, our first term, is 3 over 2. I can just throw that back into that first, the rule. A sub n is equal to 3 over 2 times 2 to the n minus 1. There's the rule. Then it says graph the first 6 terms. So let's just list the first 6 terms. The first term is 3 over 2. We know that. If the growth rate, or the common ratio, is 2, we're multiplying by 2 every time. So the next one's going to be 3. The one after that's going to be 6. The one after that is 12. The one after that is 24. And what? 1, 2, 3, 4, 5. We need one more. And then 48. So if I'm going to graph this, my graph isn't going to be very good, so you'll just have to forgive me and do better on yours. If we're going to graph this, we're going to have 1, 2, 3, 4, 5, 6 terms. So just 1 through 6 on the x-axis. The y-axis will be the values themselves. I need to go from 1.5 all the way to 48. So the first term is pretty low. We'll call that 2/3. Can't read that. The second term was a 3, so we'll say that's up here. Right, so 1's here, 1's here. The next one's at 12, so that's going to be like way up here somewhere. And there's no way I'm going to fit 24 or 48. So you can see it's kind of exponential, right? It's really taken off, which makes sense because in an exponential function, you multiply by something every time. That's exactly what a geometric sequence is. It's something where I multiply by a value every time. There's a common ratio. If we add the terms of a geometric sequence together, the expression that we create is called a geometric series. Just like with arithmetic sequences, if you add the terms together, you end up with a series. So a series is just a sequence that we're adding together. Okay, so go ahead and make sure that this formula is in your notes right here. This is just like for arithmetic, how we find the first n terms of a geometric series, to add up all the first 7 numbers or 12 numbers or 38 numbers or whatever it is. Okay, so go ahead and pause this. Make sure this is in your notes because we're going to be using it a lot. The sum of the first n terms is equal to the first term times 1 minus the ratio to the n over 1 minus the ratio. Okay, so pause and get that in your notes and then come back to the video. Okay, so we're going to find the sum. As soon as I see sum, I'm going to write down my formula so I don't get turned around. Sum is equal to the first term times 1 minus the ratio to the nth power over 1 minus the ratio. There's our formula, right? We can go back and check. Looks good to me. So let's look at what we need. I'm not going to know what the sum is. That's what we're trying to find, so no worries there. But I will know that there are going to be 10 terms, right? Because this is the number of terms up here. We're going from 1 to 10. That's 10 terms. So S of 10 will be equal to the first term. So if I plug in 1 into this guy, because this is my rule, if I plug in 1 for k, I'm going to have 3 to the 1 minus 1. Well, 1 minus 1 is 0. 3 to the 0 power is 1. I know some of you thought or said 0, but remember, anything raised to the 0 power is 1. So I have 4 times 1. The first term is a 4. Then I need to multiply by 1 minus the rate. So what are we multiplying by every time? That's going to be this guy, right? Our common ratio is a 3 to the nth power. Well, n is now 10. And just divide by 1 minus r, which is 3. So let's look back at how I got this first term again real quick, right? This is the first term. First term. I can just plug 1 in here and figure this out, but remember, this is your r value. This is your a plus, or your a sub 1. And then this is the n, or number of terms. It just changes a little bit when we put it in summation notation. I don't know why. It's just the way it is. Okay, so you can either just plug 1 in and figure out what this would be, or you can look at this in terms of this is the r value, this is my first term, and this is n. Okay, so now I have an expression over here that we can work through. So S sub 10 is equal to 4. Well, 3 to the 10th power. That's a calculator thing for sure. I'm going to do most of this on a calculator. So I'm going to go 3 to the 10th power, enter. It's 59,049. I'll write it out just so you can see it, but I would not do this separately. 59,049. over 1 minus 3 is negative 2, right? So now that I have this 59,049 in my calculator, I'm just going to hit 1 minus second answer, or you could type it back in. So that what I have now, and I'll just write it down so you can see what I'm working with, is negative 59,048, because I subtracted it from 1. I'm going to divide that by negative 2. I'm also multiplying by 4, so really negative 2 goes into 4 negative 2 times. So what I really have is s sub 10 equals negative 2 times the negative 59,048. So it's a negative times a negative. This answer will be positive. And I'm just going to take that number, multiply by negative 2, so I end up with 118,096. It's the 10th term of the sequence, of the series, excuse me, signified up here. So if I add up the first 10 terms of this rule, what we end up with is 118,096. So I guess I think I misspoke a second ago when I said this is the 10th term. This is not the 10th term. If I wanted the 10th term, I would just plug 10 in for this guy right there. Right? If I plugged 10 in for that, we'd find the 10th term. This is the sum of the first 10 terms. Okay. So here's one for you to do. 2 of them, actually. I want you to pause this and then come right back after you finish. Go. Okay. Let's write our rules here. So S sub n is equal to the first term. Now this one's kind of tricky. What is the first term? This is R. That's my rate, my ratio. This number right here is my first term. Since you don't see it, it's a 1. So my first term's a 1 times 1 minus the rate, which is 5 to the n, over 1 minus 5. So if we're looking for the sum, this tells us there are 8 terms. So I want sum of 8, which would be 1 times 1 minus 5. Oh, I think I wrote this wrong, didn't I? Let's jump back here a second. Notice that n is only on the rate, but down here I wrote it as outside the parentheses. That is incorrect. I almost messed up. Oops, eraser, come on. The exponent should only be on the 5. That is super important and will change your answer drastically. So that's the 8th term right there. Okay. So down here, we need to figure out what 5 to the 8th power is. Why is the eraser not working? So contrary to popular belief, you just learned I am not actually perfect. Okay, that's huge. I don't want one that big. Okay, 1 minus 5. I don't know why it's still showing the eraser. To the 8th over negative 4. So 5 to the 8th power, 5 to the 8th, enter, is 390,625. So I have 1 minus 390,625 over negative 4. You can just type all this into the calculator all at once. So I'm going to go 1 minus 390,625, enter, divided by negative 4, enter. And the sum of the first 8 terms is 97656. 97,656. Okay. Now, in the second one over here, let's change colors so we don't get confused. Sum of, I guess this will be the first 12 terms, right? That's what this tells us. It's equal to the first term. Now, the first term is 6 times 1 minus the rate. Now, the rate is negative 2. So if I'm going 1 minus negative 2, that's really 1 plus 2, right? However, because we have to keep the exponent just on the rate, I'm going to write it out as 1 minus negative 2 so that I can raise that to the 12th power. Okay, I hope that makes sense. The r is the only thing raised to the 12th, so I'm keeping r as negative 2 because that's actually important. Over 1 minus negative 2. So sum of 12 is 6 times negative 2 to the 12th. Again, use parentheses. Negative 2 in parentheses to the 12th is 4,096. Then I'm going to do 1 minus the 4,096 to get negative 4,095. Okay, so all I did here was take negative 2 to the 12th, found that number, and then subtracted that from 1, and that's this guy. Over. Now 1 minus negative 2 is 1 plus 2, so that's just over 3. Okay, you can do this all on a calculator, or you can simplify a little bit. I'm just going to punch it all in. I'm going to go 6 times negative 4,095, enter, and then divide by 3. Okay, so I'm going to do that right now. 6 times negative 4095, enter, divided by 3, enter. The sum of the first 12 terms is negative 8,190. It makes sense that this is negative because my common ratio is negative 2. So this sequence, as it goes, is flipping back and forth between positive and negative and positive and negative and positive and negative and positive and negative. As it's going, every number is much bigger than the one before it. So we just must have ended with a negative number to make the sum be negative. Okay. There you go. You're off to the homework. Good luck. Make sure you have those formulas down in your notes, and if you don't, rewind the video a little bit and write them down. They're going to be very important. Label everything clearly so you can keep the formulas for arithmetic sequences and series separate from the formulas for geometric sequences and series.